Alright, welcome scholars. Hopefully you're enjoying your weekend so far, assuming you're watching it over the weekend. We are going to talk about the next big thing on our list to cross off before we end off the semester. Those are, of course, our vectors. Okay, so this is a term you may be familiar with if you've taken a physics course, for example, here at classical schools. But if you don't remember, we're going to run you through it again, and we'll show you the ropes on how we deal with this in trig particularly. Okay, so first of all, what is a vector? Okay, a vector has two parts. Okay, it has a magnitude, okay, which is otherwise known as a length, okay, and a direction, which this usually corresponds to your angle. Okay, so those are the two primary components of a vector. Okay, the kind of smaller components, if you want to consider this, okay, which I'm going to star here, are the head of the vector and the tail. Okay, these things I'll talk about later when we actually get to see what the vector is. But basically, anyway, it's a thing that has magnitude and direction. And you might be wondering, well, I think I know what this is now that you described it to me. It looks like this, right? Okay, a nice old straight old arrow, nice little line, segment, array, whatever you want to call it that, where here's the point, right, and where it starts, here's the point at which it ends. Okay, mathematically anyway, this is how we represent it. Now I'm going to real quick tie each of these terms, okay, to what the picture says, so that way you can have a visualization of it. The head is right here, okay. This would be where you're ending, right, and the tail is right here. That's where you're starting. Okay. Of course, we're talking about a direction. This is what the arrow is representing. Okay. So this right here is our direction. Okay. And, you know, we can tell based on where it is in the plane what angle it is. But typically the direction and angle are the same, right? It is going at that angle, right? And finally, we have magnitude, which of course refers to the length of the whole thing. Okay, so now we got the basics out of the way. That's our four pieces of the vectors. The bigger ones to worry about are magnitude and direction. And hopefully when we talk about tail and the head, that's stuff that comes to us pretty easily. Okay. All right. So now let's talk about ways in which vectors apply to us in our trig course. Okay, so that's basics of vectors. And now we're going to talk about things like vector addition, okay, which is going to be a major part of it. Okay. Finding magnitude and direction is another part of it. And that's going to be it for most of today's stuff. So let me go ahead and take you through it. Okay, I'm also going to show you a quick little clip of what a vector actually looks like in action, because right now we don't really know, okay, what exactly separates this from array. Okay, so hopefully this little clip, okay, of one of my favorite games, Breath of the Wild, will show you exactly what a vector is supposed to be. Okay, so what I'm about to play you here is a small clip from Breath of the Wild, very early in the game. If you've played the game before, you might already know what I'm talking about here, but when we think about vectors, okay, things that we think about in the real world that are represented by vectors include things like velocity, force, things like acceleration or position, right? If I move from point A to point B, that can be represented by a vector, right? It's got magnitude, the distance I walk, and a direction. I'm going so direction, north, east, however. Okay. If you want a visualization of how, things in our world, okay, are represented by vectors as this segment, here is a clip for you to watch real quick. Okay, so first we're going to start with Link. Okay, Link's got a tool in this game that allows him to stop time and apply pressure, force, to his object of choice. So here we go. All right, and notice how when he hits it, a little arrow pops up, and he keeps hitting it, it accumulates force, and eventually it moves. Okay. So that is a really easy visualization, okay, of how vectors really work. It's got a direction, it's got a magnitude. After a bit of time, Link's little hammer lets him send the boulder flying. Okay, and that's kind of the result of him applying the vectors of force on that boulder. Let's get back to our examples, okay, so we can talk about how each process works. Okay, so before we get to the two pieces we're going to talk about here, we need to actually first talk about different ways to represent vectors. The first one, which is visually and graphically, is one I just showed you, where you see the arrow. Okay, it has an end, a tail, an end, a head, and a start, a tail. Okay, so that's very easy to understand and grasp. But what we need to know about vectors, okay, numerically, is that they use these pointy brackets, okay, where these are our components x and y, okay, which represents obviously horizontal, okay, and vertical, okay, directions. So if I say, for example, I have the vector 4, 2, that means I have a x, okay, horizontal component, a 4, and a y vertical component of 2. And they're both positive, so they should be going in the positive direction on those. Okay. If you want to think about it visually, here's what that translates to. Okay. If I start from any point in the plane, it doesn't even matter where it is. Okay. I have to count out 4 horizontally, okay, to represent my vector, and then I have to go up 2 vertically to represent my total vector for 2. This is the vector for 2. Okay. And you'll notice I did not include what the points actually were, because when we talk about vectors, they don't really matter where they begin, okay, and where they end. But what does matter about them is how long they are, okay, and what direction they're in. And this fits both of those criteria. Okay, I know how long it is. I know what angle it's at. That's all I need for vectors. Okay. You'll be able to mess around with that on Delta Math when we get to it. Okay, now let's talk about these two things down here really quickly. Vector addition is very, very simple. Okay. If I have a couple of vectors, okay, let's say I call vector v, which is going to look like that, as 1, 3. This is a very quick example. And I describe vector u, which is another way to write different vectors, as -2, 0. Well, all I have to do to add these two things together, v plus u, is just add their components up, right? So -1 or -2 plus 1 is -1, and 3 plus 0 is 3. So this is the result. Very, very simple. Okay. Mathematically anyway. I'll show you a bit later what visually looks like when we get to the examples. Okay. As for finding your magnitude and direction, this is a little more complicated. Okay. Let's use our example v as 1, 3. Okay. This is where your trig is going to happen to be very helpful to you. Okay. Remember that this is your x and that this is your y component, which otherwise refer to your adjacent and opposite sides, okay, if you remember from our trig lessons on unit circle. So let's go ahead and take a look at these. Okay. We say x squared plus y squared equals, say it with me everyone, c squared, where this, okay, refers to your magnitude. Okay, I ran out of space there. Okay, magnitude squared, I should say. All right. So when we want to solve for it, all I have to do is square root this answer, okay, and that's where we're going to get it. Right. So let's take a look. We have 1 squared plus 3 squared equals c, okay, which I will also formalize that the magnitude of a vector is usually represented by the double bars. And then we have the square root sign here. 1 plus 9 is 10, so the magnitude of v is square root 10. Okay, you'll need to be able to figure that out as well. Direction-wise, this is also pretty simple. Okay, let's take our x and y again. These are our opposite and adjacent, remember? So we just use our inverse tangent to help us find that. This is in the first quadrant, of course. It's positive, positive. So all I have to do is think about tangent inverse, okay, of the opposite over the adjacent, right? Oh, I screwed that up. This should be adjacent, sorry. And this should be opposite. That's my bad. Okay. So it's actually 3 over 1. I'm going to go to my calculator. Put an inverse tangent, 3 divided by 1. Okay. And I have the lovely answer, 71.56. Okay, so if I'm going to round it to the nearest degree anyway, that's about 72 degrees. Okay, that's my direction. That's my angle. Okay, now this is the end of the notes. Okay, I very briefly went through it. We'll cover it again in class. Let's take a look at the examples on Delta Math to see how these really apply.